This lesson talks about exploring similar polygons. You may remember from middle school that similar figures have the same shape but are different sizes. We're going to take that definition, we're going to throw it completely out the window because it doesn't actually make sense. So they have the same shape, they are different in size, but we need to talk about how they differ in size. So for example, if I had two triangles, let's say this was a 3, 4, 5 triangle, and then I had another triangle that is the same exact shape, so it would be a right triangle, and I made it a 6, 8, 15 triangle. These look like they're similar because they are the same shape and they are different sizes, and that's what the definition says, but it's not actually different sizes. We should need to change this word to be from different to proportional. And proportional just means that they are changing with the same scale factor. So if you look at this triangle, how do you get from 3 to 6? You multiply it by 2. And how do you get from 4 to 8? You multiply it by 2. But how do you get from 5 to 15? You multiply it by 3. And therefore, they are not actually similar figures. Similar figures happen if I had, let's say, a triangle. So let's say I had this triangle. Let me make this not isosceles. Let's make it scalene. If I had this triangle and I pasted the same exact one here, these would be congruent triangles. But as soon as I expand this and make it larger, I'm now scaling the triangle. That might be times 2 if I wanted to make it smaller. But notice it stays the same shape and all the sides stay relatively proportional to each other. So if I wanted to expand it back to the original size, that would be congruent, that would be similar. So similar polygons are similar if and only if their corresponding angles and their corresponding sides are proportional. So let's talk about a few of these similar figures. Are the rectangles below similar? So do they have the same scale factor to get from each side to the other? So let's see. We're going to compare 3 and 8. And we're going to see if 3 over 8 is proportional to 10 over 15. Notice that I'm going in the same direction. I'm going from left to right, 3 to 8, 10 to 15. From the last section, we learned that if you want to test out proportionality, you can either cross multiply, you could also simplify these. I find that cross multiplying is most of the time easier because I can do it very quickly. 8 times 10 is 80, and 3 times 15 is 45. And since they are not equal to each other, then these are not similar. While we're here, let's talk about the symbol for similar. It's just a little squiggly, just like we had the congruent symbol being that. They're not perfectly congruent to each other. They're sort of the same. They're similar, but we don't need the equal sign because they don't have the same size sides. Now, a lot of people like if I take this triangle, or I'm sorry, this trapezoid and rotate it. So what I'm going to do is I'm going to trace this very quickly. That's 60. Actually, let's do this first. Let me take this. Whoops. Let me move this first so that it goes like that. So that was the original trapezoid. I just rotated it a little bit so that it would be matching up here. And so then I'm going to take the 45 and I'm going to put it where it originally was, which was at the top now. And then I'm going to take the 60 and put it over here. 90 goes down at the bottom and 75 goes there. We want to see if the two trapezoids are similar, so let's set up some ratios. So we have 15 corresponding with 45. Do these all here in different colors. We have 20 corresponding with 60. We have 25 corresponding with 75. And lastly, we have the 30 corresponding with 90. I think the easiest way to do this, because we do have 4 ratios, is to go ahead and just divide these in the calculator. So if you divide all of these out, see what it gives you as a decimal. It should give you 0.3 repeating. So does this one. And so does this one. If you were to go in here and actually simplify them, these would all be converted to 1/3. But either way, they all have the same scale factor, and so they are similar to each other. So yes, they are similar. Now, if they are similar, they will have the same scale factor. The scale factor is what you have to multiply to get to the other shape. So for this one, we only have 10 and 15 in common. We don't have the question mark here. So let's say, how do I get from 10 to 15? And you're always going to read these from left to right. So how do you get from 10 to 15? Well, you simplify this and you see that the scale factor is 2/3. Now you could use the 2/3 to get this missing side. I'm just going to go ahead and set up a proportion where I know that 10 corresponds with 15, and so my missing side corresponds with 24. And since they are similar to each other with a scale factor of 2/3, I can set them equal. 10 times 24 is 240. 240 equals now 15x, and what is 240 divided by 15? It's 16, so x equals 16. If you wanted to double check this, you go in here and use a scale factor and say, hey, listen, I have this 24. What's the scale factor, or what's 2/3 of 24? And if you go in your calculator and do 24 times 2/3, you get an answer of 16. So that's how you can double check your work. Go ahead and try this one. I always like to put what I'm missing first, so that way I know I'm not going to forget it. Sometimes you don't even need to use the proportion. You could just look at the picture and say, well, how do I get from one triangle to the next? So how do you get from 14 to 7? You would just divide by 2, and from 10 to what would be the same as from 8 to 4, which is again dividing by 2. So that means that 10 divided by 2 has to give you 5. For this one, you could imagine if you took this rhombus, or not rhombus, but parallelogram, and rotated it so it went this way, the 12 that was originally up here would be rotated and put down here, and it would correspond with 6. So again, how do you get from 12 to 6? You have to divide by 2. So 5 times 2 would give you 10. Next, let's talk about some scale drawings or scale models. And we're always going to set this up using the real life to the scale. So let's say the scale drawing of an artist's work has a scale of 1 inch equals 18 inches. So in the original diagram, whatever was 18 inches long is now going to be represented with 1 inch. So if the original diagram has a rectangle on it, and this rectangle, I believe, is 5 by 6. We want to find the drawing of the original work. So in this one, we don't actually even need a proportion. You could just multiply. So for every 1 inch in the drawing, it's 18 inches in real life. So it's 5 inches in the drawing. You just multiply each of these by 18. And so the original painting must be 5 times 18, which is 90. And the original height of the drawing must be 6 times 18, which is 108. Mike has an assignment to construct a scale drawing of an outdoor chair. He plans to use the scale that 1 inch equals 4 inches. So in real life, it's 4 inches. So let's do scale to real life. The scale is that for every 1 inch in the drawing, it's 4 inches in real life. The height of the actual chair, which is not spelled like this at all, I just typed this up very quickly, is, there we go, chair. It's a difficult word to spell. Is 16 inches. How tall would it be in the actual drawing? And 16 divided by 4 gives us 4. Alan made a scale drawing of his bedroom. In the drawing, 2 centimeters represents actually 7 meters in real life. So again, scale to real life. The scale is that for every 2 centimeters, it represents 7 meters. So in the picture, his windows are 1.25 or 1 1/4 centimeters away. How many meters apart are the actual windows? So let's go ahead and cross multiply. 7 times 1.25 is 8.75. And 2 times x is just 2x. And so if you divide both sides by 2, you get that x equals 4.375. This is a terminating decimal. It ends. It does not go on forever. So it's a nice decimal, even though it's a little bit longer. Write the entire thing out. And then lastly, Tina wants to enlarge an old photograph of her parents for their anniversary. The scale is 1 inches equals, I think it's 1.5 inches. Sorry. What will the dimensions be if the photo is 2 inches by 2.5 inches? So again, scale to real life. The scale is that for every 1 inch, it's 1.5. If you wanted to, you could actually just go in here and multiply both of these by 1.5. And so 2 times 1.5 is 3. So that's one of the dimensions. And 2.5 times 1.5 is 3.75. So these would be the new dimensions of the picture. Now that you're done with this, you're going to do the go formative that's underneath here. And when you're done, just keep moving on.